Welcome back. In the previous lecture, we discussed subject of formula, how to solve equation, as well as variation. In those topics, you see the principles that guide how to arrive at your answer. The general thing that you need to do to obey. I must let you know that as a student, you have a lot of principles to learn so that you will have the best of your results. Once you know all these principles, they will be the tools that will be guiding you on how to solve any kind of problem. There are many principles that you need to learn. That's the reason why it is good for you, to be good for you, to work harder at this moment. The work that you're going to do is about just 1 year work. Devote that 1 year to your academics exercise so that you can have the best that you expect for yourself. You, as a student, it will be a very great honor to you if you don't undergo any examination malpracticing, that you'll be able to do things with your own hand and understand things at your own best. So therefore, we continue at some other things that you need to know to be very good at mathematics. This aspect is called error and approximation. It's not only limited to mathematics, it's only applicable in physics as well as chemistry. Any areas that has to do with calculation. What do we mean by error? What do we mean by approximation? Let's begin. Error is uncertainty in instruments. I will break this one down. This means that no measurement is exact. You must know that. And in order to close to the exact value, we use different approximation method. That is to say, it's because there is error that enable us, that make us to go to approximation. Without error, there is no approximation. So therefore, when you remember error, it is necessary you remember approximation. Error is an uncertainty in measurement. For example, let's assume that you have a ruler, your normal ruler that is calibrated. I may not draw it very well, I'm so sorry. Your normal ruler, and you want to use it to measure the length of a book. Of course, you may get the length of the book to be anything, but what if this ruler is wrongly calibrated? What if this ruler has bent at one particular point? And what if internal contraction and expansion have changed the actual length of the ruler? This is what can lead to error in measurement. That is the reason why for any student that want to understand the principle of measurement, you must understand the principle that guide the usage of your instrument. And I must let you know, in order to understand the rule that guide your instrument, you must understand the principle of calibration of instruments. Every instrument that has value and line are calibrated. Therefore, each of these lines on that instrument have particular value. And the value that is awarded to each line, the value that approximates to the value that is indicated for each line is called the accuracy of that measurement instrument. So the accuracy, it is the value of each single stroke that you have on your measuring instrument. If you take your ruler, you are going to see those strokes and you will be able to see their value. For example, look at this syringe here. You can see that there are strokes on this syringe. And for this syringe, what is the accuracy? This stroke here mark point 0. This is 1, this is 2, this is 3, this is 4. Look at between 0 and 1. How many strokes is there? 0, 1, 2, 3, 4, 5. There are 5 strokes in between value of 0 and 1. You start counting from 0. There are 5 strokes between 0 and 1. In order to know the value of each of these strokes here, you need to do this calculation. You need to know the number of strokes between two adjacent values, 0 and 1, or 1 and 2. So normally you choose 0 and 1. Are you getting me? Yeah, and if you like, you can count the stroke between 1 and 2, but you must start from 0. For this layer, it's 0, 1, 2, 3, 4, 5. So you have 5 strokes between two adjacent values. You take the difference of that value, which is 1 minus 0, or 1 minus 2, or 2 minus 3, anyone that you like. I said that 1 minus 0, that is what? 1 divided by number of strokes. So this calculation is known as accuracy. And accuracy means value of each stroke. In this case, I have 1 divided by 5. So 1 divided by 5, you know the value, that should be approximately equals 0.2. So the accuracy of this syringe is what? Is 0.2. So this accuracy represents value of each of these strokes. And if you want to note it, this one is 0, this one is 0.2, this one is 0.4, this one is 0.6, this one is 0.8, while this one is 1. You cannot see that value of each stroke is 0.2. So by doing that, you'll be able to know the accuracy, which is the 0.2 value of each stroke. To know the error is equal to the error that may likely to occur on this stroke, on this instrument, is the value of each stroke divided by 2, which is 0.2 divided by 2. That is half of the value of each stroke. I get me? That is the possible error that can occur on this particular syringe. And you know that this syringe measures liquid in ml, which is the volume of the liquid in it. Therefore, whenever you take any measurement, maybe you take the measurement to be equal to what? 5.2 mil. Are you getting me now? If the measurement of the value of the volume of liquid that you got is 5.2 mil, you have to indicate error, which is equal to what? 0.02 divided by 2. If you look at that, you are going to get possible value of around 0.5. I mean, if I'm mistaken, sorry. 0.2 divided by 2, you are going to get something like 0.05. So, let us now see, with respect to that, what is the meaning of cutting each of these particular value with with their error? So you will have to see that, okay, we say that 0.02 divided by 2. So answer should be equal to, let me see, okay, this should be, let me multiply this one by 10, and multiply this one by 10. I will have 2 divided by 20. So 2 divided by 20, that is equal to 0. So that is equal to 0.1. That is 0.1, sorry. So the error here is accuracy 0.2 divided by 2, which is equal to 0.1. So you cut your value to plus or minus 0.1. This is error that may arise. That is to say, the value can increase by 0.1 or it can decrease by 0.1. But in many of our real-life measurements, of course, we don't really care about this particular error that can occur. And this error enables us to take what we call accurate measurements. But many of us, we leave it out and we go to what we call approximation. An approximation is to give you something that will be very close to that particular real value. There are many ways approximation can be taken, and one of them is nearest value, decimal places, significant figure, decimal place, significant figure, and standard form. Now, we see that there is error. And because of the error, we discuss the concept of accuracy, which is equal to what? Value of each stroke on any calibrated instrument for measurements. And we say that the error is equal to what? Half of the value of that accuracy. And we point to it that for any measurement, we are supposing to be taking the value of measurement alongside with the error that can arise. But we say that we don't go into that. Many people neglected that and go to what we call the procedure of approximation that enable the taken value to be very close to the exact value. So in this case, we want to discuss nearest value, decimal value, decimal place, significant figure, and standard form. Now, what is very important at each of these points is that each point will be telling you their errors. And from that, you should be able to calculate absolute error, relative error, as well as percentage error. These are the three types of errors that you need to know for now as fundamental knowledge. Absolute error, relative error, and percentage error. I will teach you will see the formula for each of these following. Normally, errors are defined according to each of these approximations. So before you take note of your error, look at the type of approximation that you have. Are you getting me? But basically, absolute error, that's known as what? The real error itself is equal to real value minus observed value. Real value means the actual value that it is the original value of the measurement. Observed value means the value that you measure, the value that you take. And of course, real value can be given in different ways. You may be given directly, or you may be asked to figure it out. And of course, if you take a series of measurements, let's say that you measure something to be 2.2, you measure it to be 2.3, you measure it to be 2.4. The real value of these three measurements is the average, while the observed value is the each value. And you can calculate the error by taking each value away by taking the actual value from the real value. So in this case here, you will take the absolute value, which is the positive number. Of course, it can be positive or negative. But if it's either positive or negative, you are going to report the positive number. That's the reason why we put this bar to represent absolute value, which is the positive value of our error. Now, in this case, it is absolute error because we take the positive value. It is the half of the least of measuring value. It is the half of the least of measuring value. The least measuring value, it is the value of each stroke, which is the accuracy. Or half of the nearest round off. Half of the nearest round off. Or Difference between true value and measured value. You have seen three methods by which absolute error can be known. Number one, half of the what? Half of the least value of the measurement, or half of the what? Nearest round-off value if you round it off, or difference between true value and measured value. Note the following. Fraction is a relative value of one number to another. And there is a reason why we stipulate this particular number. Now, we have error. We have seen the definition of error. That error can come in different methods. In this slide, on this slide, we identify three methods. Half of the least of value of measurement, which is the what? Half of the accuracy. Half of the what? Rounded off, if you round off, as well as what? Difference between real value and measured value. Just note which one that you are given. We are going to see how to apply this thing. Now, this is the formula for relative error and percentage error. What is relative error? It's a fraction. Can you now see the reason why we make reference to fraction? Fraction is a fraction. And it has to do with what? Measured value minus real value. Let me give you one particular very important key about this fraction that we are talking about. This fraction normally take value with respect to original. With respect to what? Original. If it is not original, we can call it initial. We can call it initial. If it is not original, we can call it initial. Don't worry, we are still going to discuss the ratio, proportion, percentage, as well as loss and gain. This is the area where this thing is very, very important. But note that whenever we are talking about fraction, the denominator here is resembling original or initial. Let me state for example. Before you can lose, before you can incur loss, there must be two things on ground. You have to sell and you have to buy. Between selling and buying, which one are you going to do first? You cannot sell what you have not bought. Therefore, you have to buy first. And the amount that you buy something is called cost price. The amount that you sell something is called selling price. So whenever you are looking at fractional loss, so the denominator is going to be the what? Initial price, which is what? Cost price. So in this case, for the error, the initial price that we are going to have, it is the original, which is real. The relative error will now take error, and the error is equal to what you measure minus the what? The real value. That real value for group of measurement is called mean value, and the one that you measure is called the individual value. You take their differences. When you take their differences, you take the absolute value, which is absolute error, which is positive value, and you divide it by the what? Real value. That is the what? Relative error as well as what? Percentage error. For percentage error, is equal to what? Relative error multiplied by 100%. Are you getting me? Now, the first thing that we are going to discuss is called nearest value. Many students get this aspect wrong because they don't remember their primary Cs. I want you to pay a close attention, please. I want you to observe this thing closely to see what we want to explain at this point. When we are saying that nearest value, What is the meaning of nearest? Something that is close. Closest. Value is a digit. We want to look at the nearest digit, closest digit. But before you can understand this thing, there is something that you must understand. Now, let us see. Number place is what you need to understand before you can understand nearest value. And when we are discussing the principle of concept of number placement, what is the meaning of that? Let's take it for example that they give you 1050. Each of these digits fall under particular number template. 1000, one fall under 1000. One fall under 1000. But there is a problem because this one is 0. The number standard for this thing, the number base for this thing, which is the base value of this number, the standard value of this number will not be pronounced because this one is 0. But let us change this one to 2 so that that number can be pronounced. We now have 1250. 1000, the proper pronunciation is 1250. That is to say, these two fall under 100. One fall under 1000. Two fall under 100. 1250. So what is 50? Let us change this one to a particular value. Let us make it 2. Let us make it 2. So it will now become 1252. What is the place value of this? What is the place value of this? The place value of this is 10. That's the reason why 5 multiplied by 10, it is 50. 2 multiplied by 100, it is 200. 1 multiplied by 1000, it is 1000. And unit is what? 1, 2. So the standard base value for these numbers, they are power of 10. This one is what? 10 raised to power what? 3. This one is 10 raised to power 2. This one is 10 raised to power 1. This one is 10 raised to power 0. And anything raised to power 0 is equal to what? 1. That is the reason why we give you this thing on this table here. Look at 1 million. This is 10 raised to power 6. 100,000. This is 10 raised to power 5. 10,000. This is 10 raised to power 4. 1,000. This is 10 raised to power 3. 100. This is 10 raised to power 2. 10. This is 10 raised to power 1. Unit. This is 10 raised to power 0. Decimal place. That is decimal point. Tenth. This is 10 raised to power minus 1. 100. This is just 10 raised to power minus 2. You can see tenth. You can see this TH ending. You can see this TAHS. You see? THS ending. THS ending. So that is my negative index. 10 raised to power minus 3. So this is the standard base that each number will fall under. Let us now look at this number here. 1768.82. Let us now pronounce 1768.82. Why can't we call this one 82? It is not 82. It is 0.82. Any number after decimal point, you pronounce them one by one. because their index is negative. Is that clear? Their index is negative. Okay, let me now put a number here. Let me put 8 here. Let me put 4 here. Let me put 3 here. And pronounce all things together. This is 1 million. Is that not it? 4 multiplied by 1 million. 4 multiplied by 1, that is 4. This is 4,800,000. That is so 4,883. In fact, 800,000. 3 multiplied by 10, that is equal to what? 30. This is 30,000. 1 multiplied by 1,000, this is 1,000. 7 multiplied by 100, this is 700. 6 multiplied by 10, this is 60. And 8 multiplied by 1, this is 8. So, and we say that whatever digit that you have, start counting behind 3 numbers at a time. 1, 2, 3. You put comma there. 1, 2, 3. You put comma there. So this is 4,831,768.68. You must know the place value of every digit in a number before you can understand nearest value. And now, you can say that each of these numbers multiply their base. 4 multiplied by 1 million, that is 4 million. 8 multiplied by 100,000, that is 800,000. So in the number pronunciation, each digit multiply their base. And we use 10 in this place because the standard base for our calculation here is base 10. If it is base 2, all the 10 in this place is going to be 2. If it is base 3, everything in this place will be base 3. That is the standard method of how arithmetic combinations are done with respect to number base. Now, there is something that we need to know at this point. And it's about how approximation is done with respect to nearest value. Are you getting me? So we have given us this number here, 1,768. 1,768 to nearest 1,000. To nearest 1,000. Now, to nearest 1,000, you are going to look at the number that fall under base of 1,000. Are you getting me now? That is where you are going to stop. Let us see which one fall under 1,000. Yes, it is 1 here that fall under 1,000. Look at this number here. Since this number is greater than 5, you will approximate it to 1 and add it to this. Any number after that 1,000 will be 0. Any number after that base of 1,000 will be 0. Now, in this case, because this one is greater than 5, immediate number after that inference number, the number that we refer to here, it is the number under the base of what? 1,000. The number that follow it immediately, if that number is greater than 5, you are going to approximate it to this. But let's assume that this number is 4. Don't mistakenly say that you approximately this is to this, and you no, don't do that. Now, in this case, this one will become 2, and the answer will be what? 2,000. Are you getting me? Are you getting me? 2,000. Now, what is error? The error is what? The rounded off value. Look up. Look at this place. Half of the nearest round off. The nearest round off here is what? Is round off to the nearest what? 1,000. The nearest round off here is what? 1,000. Then the error is equal to what? 1,000 divided by 2, which is 500. That is the error. Look at the second one here. That second one said that we should round it off to nearest 100. Which number fall under 100? 1,700. So 7 fall under 100. And look at the numbers that follow it immediately is greater than what? 5. So this one will become 8, and all other number after that 100 will become 0. So nearest 100, answer is what? 1,800. And the error is equal to what? 50. Nearest value divided by 250. But nearest 10, which number fall under 10? This is 7. That's why this particular 6 fall under 10. Number that follow it immediately is what? 8. So you approximate it to become 7, 7. Any number after that 10 will be 0. So it's now become what? 1770. And the error is what? 5. This one divided by 2. But if it is to nearest unit, nearest one is equal to nearest unit. So nearest unit, look at this number. Any number after nearest unit. So this is the number that they refer to. So it is equal to that number. And the error is equal to what? 1 divided by 2, which is 0.5. So every number here, every number in universe have error of 0.5 initially. Have error of what? Plus or minus 0.5, because the last number here is nearest to what? Unit. Are you getting me? It's nearest to unit. They may give you a particular number and they may ask you to find its error. If you are not given any nearest value, the nearest value of that number is unit, and its error is equal to what? 0.5. I have said it. Now look at this number here. 17.3 to nearest, you see, to nearest what? 1,000, 1 over 1,000. The one that is the 1 over 1,000 here is what? This is 10. Is that not it? You see, it begins from 10, and this is what? This is 1,000. Are you getting me? This is 10. This is 1,000. No, sorry. This is 10. This is 100. This is 10. This is 10. This is 100. This is thousands. You see? So this is where we are going to stop. And because this one is not up to 5, we don't approximate it. So the answer will be equal to what? 17.356. And the error will be equal to what? All of this divided by 2. So the same thing occurred to this place, the same thing occurred to this place, the same thing occurred in this place. Are you getting me? So sorry, this one is going to be decimal point. So I think this one is not here. Do not include this one. Please. Do not include this one. So this is where we stop. Are you getting me? To nearest tens. So this is the tens. You approximate it to this is equal to 4. Please, if you don't understand this concept, watch this video again and again. And watch the points that we have made. So decimal places now. After number place, it remains a decimal place. What is decimal place? You will see a decimal point. Are you getting me now? So any number after decimal point is what we are talking about. You know, in previous class, nearest value, it consider every number. It consider every single digit in the number. But decimal place consider digit after decimal point. Decimal place consider digit after decimal point. So now, this is the number after decimal point only. This is done by retaining the number after the decimal point to indicate the decimal digit, such that 1 is added to the digit in the indicated decimal digit if the number after it is greater than 5. If the number after it is greater than 5, don't worry, you are going to get what you are saying. Look at the example here. You understand this concept because we have explained it initially in the previous slide. So look at this. 70.3564 to the 3 decimal place. To 3 decimal place. That is 3 number after the decimal digit. So it will be equal to what? This. That is to be equal to what? 3.56. to 2 decimal digits, that is 2 number after decimal point, is going to be what? 17.36. To 1 decimal place is going to be what? 70.4. Are you getting me now? Just look at how many number that they want you to retain after decimal place, and they will state it. In this case, this means that to 3 decimal place, that is to say, retain 3 number after decimal point. To 2 decimal place, retain 2 number after decimal point. To 1 decimal place, retain 1 number after decimal point. So significant figure. What is the meaning of significant figure? They are the digits that are significant in a value. They are the digits that are significant in a value, that you must not remove them for that value to be very close to the exact value. Now, this is the number of digits to retain in a value by adding 1 to the last digit if the number after the last digit is greater than 5. Now, let us see. Significant figure can be done using a set of what? Around 5 rules. What is the meaning of that? With a lot of complication for how to deal with zeros. But there are some rules that you need to understand. For you to understand significant figure, to know the number of the significant digits, you need to understand basic number like this. Look at this basic number. This is 0.004 Sorry. So we are trying to look at which one are significant. Are you getting me? But let us go. This zeros has been labeled. Look at this 0 here. For the cosmetic purpose. For the what? Cosmetic purpose. Not significant. Not significant, significant. 0 used only to locate the decimal point. That's not significant. Cosmetic 0, not significant. 0 used to indicate decimal point, not significant. You see, this one is not significant, this one is not significant. Then, but 0, all 0 between non-zero value. All zeros between non-zero value. This is non-zero value, this is non-zero value. All zeros between them are significant. And is 0 after non-zero value. 0 at the end of number to the right of decimal point. So is 0 to the any zero to the right of the decimal point is also significant. Any 0, I repeat, zeros at the end of a number, at the end of a number to the right of this decimal point. Let me make this thing clear. You need to know it, please. Is zeros at the end of a number, there must be a number, and this number must not be 0 number. It must be non-zero number. You see that this is a decimal point. This is left. This is right. Let us now see if there is a number that is non-zero to the right and there is 0 after it, all that zeros to that number are significant. Are you getting me now? But let's assume that, okay, to the right of the decimal place, to the right of the decimal point, what you have is 0, and another is 0, another is 0. All of these zeros are non-significant because there is no non-zero value before them. Please, these are the principles that you need to understand. Just how many? 1, 2, 3, 4. When it comes to significant figure, which one is significant? 0 between non-zero digits and 0 after non-zero digits after decimal point. Those zeros are significant. Look up. If they give you something like this, 0.0002, you now say that, okay, round this thing off to 2 significant figure. Round this thing off to 2 significant figure. Some most students will say answer is equal to 0.0. Please, is this one significant? Is this 0 significant? Tell me, they are not significant. Answer is equal to what? 0.002. And you must put 0 because is 0 after this digit is significant. So now you have your two significant figures. If you don't put this 0 and they ask you two significant figure, I'm so sorry, you are on your own. That is the reason why you need to understand the basic principles. So, aspect of significant figure has been clear now. Just understand this set of 4 basic principles. 1, 2, 3, and 4. Now, significant digit rule, we have said it. There is no need for us to repeat it. This is just a repetition. Now, these are some examples. Are you getting me now? Let me use my white chalk. Is 0.00768 is equal to what? Is 0.00877 to 3 significant figure because all of these are not significant. So 1, 2, 3 are significant. But let's assume that this number, there's nothing here. It is just 8. And they say that 3 significant figure. After this 8, you need to put 2 zeros. 1, 2. Are you getting me now? But since there is a digit here, there's no need for that. Another one is this. This is 8.9.34. This is 3 significant figure. This is 3 significant figure. This is 3 significant figure because all of these numbers are not 0. Are you getting me now? Since they are not zeros, all of them are significant. So if they ask you to round up this number to 3 significant figure, all of these are significant. So the remaining, you abandon it. If this one is not up to 5. So this one as well to 3 significant figure, this one as well to 3 significant figure, what do you have to do? Approximate this one to 1. So you have your 3 significant figure. What about this? 3 significant figure, 3 significant figure, approximate this one to 1. You have this 3 significant figure. And I believe you have understood the concept of significant figure. Now, there is standard form here. What is the meaning of standard form? The general template for standard form is a number multiplied by 10 raised to power plus or minus any other number. A is any number, P is any number. Any number can be converted to standard form. Follow the rule below. This rule, I think you need to understand it. For any number in universe, there is always a decimal point. If you write 20, answer is 20 decimal points. 0. We just don't put that 0 to not complicate issue. Are you getting me? Even if you have a non-decimal point 0, there is decimal point after the last digit. In order to now do standard form conversion, you need to follow some certain rules. Identify where there is decimal point. Identify where there is decimal point. Move to the left. Move to the right, sorry. And also move to what? Move to the left. These decimal points, do you know that's a negative value, but you don't know? If I draw negative sign like this, that is negative sign. And I erase it a little bit at a time. Oh, sorry, that one cannot work. And I erase it at a time. You will see that I will get to that decimal point. I will get to that decimal point. But yeah, now look at what you have that is left here. That is the decimal point. What I want to tell you here is that a decimal point is derived from negative by reducing the negative to very tiny point. That is to say, this decimal point is a negative sign. When you move to the right, you move to the positive direction. When you move to the left, you move to the negative direction. And when you are moving, you are moving between numbers. You are moving what? Between numbers. And the number of steps you move, you must count it. Then you multiply the sign of the point with the sign of the direction. That will be the sign of the index of 10. That will be the sign of the index of 10. The meaning of that is this. Let us see. 20. Convert it to standard form. If I want to convert this one to standard form, I will know that, oh, my 20, the decimal point is here. Is that not it? The decimal point is here. And I can put a 0. Are you getting me now? I will move to the right of the decimal point. I will also move to the left of the decimal point. If I cross the first number to the left, are you getting me now? The number of time I have moved is 1. And I have negative multiplied by negative. Negative of decimal point multiplied by negative of the direction. That's what? Positive. That is to say, I will have 2.0 times 10 raised to power 1. It means that one means that I move only once to the left. If I move to in front of any other digit, do you see? My decimal point will now be in front of what? Will now be in front of 2. So I will now have is 0 point what? 2 is 0. How many times do I move? Times 10 raised to power 2. So I have converted this thing to decimal point in what? In index of raised to power 1 and index of raised to power 2. But in normal life, they always remain one digit. So that is to say, this is the best standard conversion. You will remain one digit. Are you getting me? So look at this one now. Convert this one to standard form. I want to move the decimal point to the front of 5. And let me count. This is what? 1, 2, 3, 4, 5, 6. I have moved 6 times to the right. And to the right is negative multiplied by positive. That is negative sign. That is to say, I will be having 5.3 times 10 raised to power what? Minus 6. Because plus times minus is minus. That is it. So what about this one? I will be moving to the what? To the left. 1, 2, 3, 4, 5. So this is what? 1.5. You leave one number, okay? 1.5 times 10 raised to power 5. So this is the principle of converting a number to a standard form. And any number can be converted to standard form. Now, these are some exercises that we need to do. Correct each of these following number. Correct each of the following number to 3 significant figures and multiply them. Give your answer to 2 decimal place. So there are 2 numbers. Convert them to 3 significant figures. This one is what? I have this one because this 3 number is significant. What about this? This one is not significant. 1, 2, 3. So this is the end of this one will now be what? 7. So this is equal to 7, 4, 7. It will now be what? 0.0747. So let me take my white chalk. So in that case, I have 59.8 multiplied by what? Multiplied by 0.0747. The calculator of paper that you are going to be given in your UTME can undo this calculation. But I will implore you to be conservative with calculation without calculator. We are still going to talk about that. But for now, let us maintain this level. That's to say 59.8 multiplied by what? Multiplied by 0.0747, 0.07, 0.0747. What is answer? Answer is equal to what? Answer is equal to 4.46, 4.46 and 4.46706. But what is our answer? Answer said, give your answer to 3 significant figure, and these 3 numbers are highly significant. But you can see that after 6, the next number is 7. Are you getting me now? So we must approximate this one to 7. So the answer is what? 4.47. 4.47. C is the correct answer. So reduce each of these number to 2 significant figure and then evaluate. Reduce them to 2 significant figure. The 2 significant figure here is what? Here, you see, is what? 0.022. Because you approximate this one, because we have 2 significant figure there. And this one is what? This one is 1.2 multiplied by what? 1.2. Yes, divided by what? 2 significant figure. This is 0.024. So 0.024. So calculate your value. You are going to get your answer. Now, instead of writing 5/6 as a decimal, correct to 3 significant figure. A student wrote it correct to 3 what? 3 place of decimal. Wow. As a decimal. Okay. As a decimal, correct to 3 significant figure. A student wrote it to what? 3 place of decimal. That is 3 decimal place. Find the error. In order to find the error, you need to know the actual value minus the what? The observed value. And of course, if you look at 35 divided by 6 as correct to 3 significant figure, the answer is what? 35 divided by 6. Check it out. Answer is equal to 5.83333. But what do we need? We need only 3 significant figure. This is going to be what? 5.8. Sorry. Okay. So, okay. So what do we have? We have, yes, 5.833. But we need 3 significant. So this is the 3 significant figure. But the student wrote it correct to 3 decimal place. 3 decimal place is what? Look, 5.833. That is 3 digits after 3 decimal place. So what is our error? Our error is equal to what? Observed value minus what? Exact value. This is equal to what? 5.833 minus 5.83. What is answer? What is answer? We are 5.833. 5.833 minus 5.83. What is your answer? Your answer is equal to what? 0.003. But your answer is to be what? Error. You will find the error. This is your error in standard form. So what is your standard form? We are move it. 1, 2. Is that not it? You still have 0 point, then 3. You must have 1 number. Are you getting me now? You must have 1 number. So this is equal to what? 3 times 10. 3. So if you put anything here, it will be 0.0. Are you getting me now? 3.0 times 10 raised to power minus what? How many times do you move it? 1, 2, 3. That is minus 3, because plus minus times plus is equal to minus. So that is direction. Answer is equal to what? 3.0 times 10 raised to power minus 3. 3.0 times 10 raised to power minus 3. B is your correct answer. If a rod of length 250 centimeter is measured as 255 centimeter long, so what happened? There is error of 5 centimeter. What is the percentage error? Percentage error is equal to what? Error all over actual value Is that not it? So multiply by 100%. So multiply by 100%. So what is error over actual value? So error is equal to what? 5 divided by what? 250. So multiply by 100. Answer is equal to what? 2. So that is your error. So this is the end of this lecture. We are going to continue discussing the other area in mathematics in our next class. But today, you have seen it that you have understood the reason why we talk about error and approximation. And you have seen the 4 basic approximations that we are using. You also understand number placement, which is number placement. Place number under its own base. So thank you for listening. We are going to meet in the next class. ABP.